Hello everyone, welcome to chapter 2. In this video, lesson 2.1, we will study about the some basic functions. In this chapter, we are studying about functions. In this particular video, we will look at the graphs of some basic functions and we will study a concept called continuity. When is a graph said to be continuous? When is a function said to be continuous? And when it is not continuous? We will discuss those ideas. And the good news is this particular video, this few pages that we will do are relatively straightforward, very intuitive. You can see and you can recognize what it is. Not a lot of calculation. It is more kind of understanding and very intuitive. When I say intuitive, I mean common sense. Whatever your common sense says would be the right thing. Okay. Maybe we'll just focus on learning the correct terminology. What is the right mathematical word to describe what we already know? Okay, just by looking at it. So let me begin. The definition, right at the beginning, continuous function is what you think it would be. If I can draw a graph continuously, it represents a continuous function. Now, what do I mean by drawing continuously? I should be able to draw it without lifting the tip of the pen. Okay, and I'm going to write that here. A function f of x is continuous if it can be sketched without lifting the tip of the pen. Okay, that is the definition of continuity. Now, in other words, now that sometimes you might think is not super clear. A continuous function lacks some things. Okay, in a continuous function, you will not find no jumps. That means you don't, you are not going and then suddenly jumping to a new value. It has to be continuous, and it has to be, the transition has to be continuous. So no jumps, cuts, no cut in the graph, holes. Okay. And vertical asymptotes. Now, what are each of these things? We will be seeing in the pictures below. A continuous function will not have these things. Okay. Let us look at discontinuities. So, a continuous function does not have these discontinuities, right? What makes a function not continuous? We are going to look at that. Firstly, a vertical asymptote. A vertical asymptote is where the function is going towards infinity. Okay, the values of the function are going to infinity or minus infinity. As you see in the graph there, on two sides. On the left side, it is going to minus infinity. On the right side, it is going to plus infinity. Either one of them, it does not have to be both. Remember that it does not have to be both. One of them, any one of them is true, then it is a vertical asymptote. Now that means the denominator is 0. The value of x for which the denominator is 0. If the denominator is going to 0, then the fraction goes to infinity, right? I will write that here in the language of mathematics. We write like this: 1 over 0, okay? And I will indicate a notation, okay? Plus. That plus is there to indicate that it is a positive value, like 0.0001, like that, is going to or goes to plus infinity. And 1 over 0 minus. Now the minus there indicates negative value, okay, like minus 0.00001. 0, so it's very small, but minus, negative, okay, very close to 0, but on the negative side. That goes to negative infinity, okay. Some of you might be taking calculus in the future and you will be encountering or using this terminology more often. But for everybody, these are something good things to know, okay. If you divide 1 by a very small positive number, 0.0001, it is very large, that is plus infinity. If you divide 1 by a very small negative number, like minus 0.00001, then it becomes a large negative number, that is minus infinity. Okay, just get that. That idea is what we are using here to get a vertical asymptote. Okay. And in the description here, you will see the value of x for which denominator is 0. And I should add something, okay? And numerator is not 0. So for the value for which the denominator is 0, but numerator is not 0. Okay? Denominator is 0, but numerator is not 0. Then it is a vertical asymptote. So for example, 1 over x plus 2. Okay? So if for 1 over x plus 2, if you plug in x equal to minus 2, then you have a problem, right? Can you plug in x equal to minus 2? Let me put a question mark there. If you plug in minus 2, you'll have 0 in the denominator. And then you see in the graph here at minus 2, you have the vertical asymptote. All right. Now, that is like in one reason or one of the situations where a function is not continuous, discontinuity. And for such a function, the domain would be, now domain is the values of x which can go in, which you can plug in the function, okay? Plug into the function. Now clearly we cannot plug in minus 2, right? So in the domain, you have to avoid the minus 2. How do you avoid minus 2? You say it is from minus infinity all the way till minus 2, but you put a parenthesis. You know, parenthesis means you are not including that. So minus 2, just before minus 2, but not exactly minus 2. Parenthesis. And then you use this symbol, which is called union, right? I have talked about this before. Union minus 2 to infinity. So think about that. We are just avoiding the minus 2. Okay. And everything else on the left, everything else on the right. That is your domain. And then next part is increasing, decreasing. So what we have to fill in there is, if you look at the graph, in which part of the domain is the function increasing? Increasing means as you go from left to right, its value should be increasing. Okay. And decreasing is as you go from left to right, it is of course decreasing. Now, the funny thing you notice here is, we can say DNE. Look at the graph. It doesn't increase ever. If you look at the left side, you are at 0, close to 0, and minus infinity, and but you are gradually decreasing and you are going to minus infinity. Whereas just after minus 2, you are starting with infinity and then you are gradually decreasing to 0. So this graph is never increasing. If you take calculus later, actually we'll see one more reason, from derivative, we can actually prove that this function is never increasing. Okay, like algebraically, without the graph, we can prove it. Now decreasing everywhere. So everywhere, but that means everywhere in the domain. Okay, so minus infinity to minus 2, union minus 2 to infinity. So this is an interesting function which is decreasing everywhere in its domain. Okay, moving on. The other reason a function would be discontinuous is when there is a hole. Okay, if you look at this graph bottom below here, at the point corresponding to 0 1, at 1 comma 2, the point here 1 comma 2, actually that point is not on the graph. There is a hole, it's not defined. And why is that the case? Because you see that in the given function, the denominator, right? When you plug in x equal to 1, that becomes 0. But now you think. Previously also we had a similar situation. There was x plus 2 in the denominator. But at that time, why did we not get a hole? And here, why are we getting a hole? The situation is similar, right? The difference now is, in the previous function, the numerator was 1. So you did not have a x plus 2 in the numerator. You just had 1. But whereas you have that x minus 1 in the numerator here. Okay. Now some of you are wondering, I don't see a x minus 1 in the numerator, but I'm sure if you give a thought, you can now see there is actually an x minus 1, right? How? That x squared minus 4x plus 3, I'm sure you know this factoring from your high school. If you do not, if you need help with those kind of algebra, please reach out to me. I'll be more than happy to help. Come to office hours. Okay. So the numerator can be factored as x minus 1 times x minus 3. So there is an x minus 1. When that happens, now this is important, okay? When that happens, there is a factor in the numerator as well as denominator. You get a hole in the graph. All right. And actually, the rest of the graph, would be like y equals minus x minus 3. That's the rest of the graph, basically. Other than the hole, before and after, on both sides of the hole, it's the straight line. You can say it's a straight line whose equation would be y equals x minus 3, which would be the case if you were to cancel the x minus 1 from the function there, from the rational function there. Okay. Again, now what's in the domain? That's the same. Okay, the logic of the domain is same like before. Now you have to avoid 1. So please go ahead and write the domain and then check with me. And this time we are also writing the range. Now, in the similar to domain, see what is missing in the range. In the domain is on the x-axis, right? 1 is missing. What is missing in the range? Please write it for yourself first and check. 2 is missing from the range, right? That's the hole there. Okay. Moving on. The yet another type of discontinuity is a jump. So in this case, you are not you don't have an asymptote. It may not be a hole necessarily, but the values of the function are suddenly changing. Like if you look at the graph there, it is going at a linear rate, then it is suddenly jumping and again continuing. But the problem is where exactly that transition took place, it is not continuous, right? Remember earlier what we wrote? I cannot sketch that graph without lifting the tip of the pen. Okay, so this kind of discontinuity is called a jump discontinuity or a gap discontinuity. And typically, typically it happens with what we call piecewise functions. Piecewise, the terminology piecewise is these are pieces of the domain. Okay, this means from minus infinity to 2, right? Less than 2. That's one piece. This is from the second part is from 2 to 4. Notice square bracket and 2, parenthesis and 4. Equal or greater than 2, less than 4. And the final part is from 4 to infinity. So these are three pieces of the domain, and the function has been defined piecewise. In each piece, it has a rule, and the rules are different. In the first piece, it is x minus 1. In the second piece, it is half x plus 2, and so on. When a function is defined like that, we call it a piecewise function. Okay. And in this case, when you write the domain, you have to write the whole, not piecewise, but put together. If you take all the pieces together, what's the domain? Okay. Check carefully. The function is defined for x less than 2. The function is defined at 2 and up to 4, then at 4 and greater than 4. Basically, there is no point on x-axis where the function is not defined. And I want you to confirm this very carefully both ways. Look at the definition, the piecewise definition that is given, and check that you are not missing any number in that definition there, right? When x less than 2, 2 equal or 2. Like for example, if it was x less than 2 and the second function was x greater than 2, then you would have missed 2, right? We have not done that here, okay? The 2 is not left out. I want you to confirm that way. And I also want you to confirm by looking at the graph. Both these skills are important, okay? If you look at the graph, you will see that there are solid those dots at 2 as well as at 4. If both, below and like the lower end of the line and the where it starts next, and if both of them were holes, then that would have been a missing point from the domain, right? But both at 2 and 4, one of the endpoints is full or solid, not whole. Okay, so everything is included. So basically, domain is everything from minus infinity to infinity. Okay, and what about range? Now, you can maybe figure out the range by again from piecewise definition. That is one way we can find the range. But that might be a little bit challenging for many of you at this point. You can look at the graph. That will be easier. Okay. See the graph and try to find out what are the values of like y. Just like domain is for x, what values do you see on the y-axis that correspond to the graph, and what is missing? Okay, give a thought. And I'm inclined to think like this. Because the left side, x minus 1, the first part of the domain, that is a line going down, right? So you can start all the way from minus infinity. If you continue to left, it will go, more and more negative below the x-axis. So but you stop at just before x equal to 2, which means x minus 1 will be 1. Okay, that is one thing. Then between 2 and 4, your value is half x plus 2. Now when you plug in half x with x equal to 2, this part here, okay, let me write that. When you plug in that, half times 2 plus 2, that becomes 3. So union, you are starting from 3 and actually it's equal or greater than. So let me actually put a square bracket, right? And we are going till 4. When you plug in x equal to 4, similarly, you get half times 4 would be 2 plus 2, 4. So you are going from 3 to 4, but 4 is not included. Or just look at the graph. Like in the graph, you can see the lines 1, 2, 3, 4, count it on the y-axis. From 3 to 4. Just 1 second, sorry. What did it? 1, 2, 3, 4, 5. What did this do? 5. Half x plus 2. When you plug in x equal to 2, you get 3. When you plug in x equal to 4, you get 2 plus 2, 4. Okay, so the graph is not accurate. Okay, so I noticed something here. If you just try to read from the graph, there is a little problem. When you plug in x equal to 4, you get the output is 4. Okay, actually, let me show it here. This one. When you plug in x equal to 4, it is half 4 plus 2, which is 2 plus 2, which is 4, but not included. Okay. So in the graph, it looks like it is going all the way till 5. 1, 2, 3, 4. Yeah, that's not correct. Okay. It's going from 3 to 4. And then there's one more value, which is the last rule. Okay. Y equals 2 for x equal or greater than 4, right? That's only one value, constant function there, 2. And that we are not writing as an interval. We are just writing the number 2 in the set bracket. That's the range. Everything from minus infinity to 1. Then just the number 2, nothing. Okay, between 1 and 2, other values are not included. Even 1 is not in the range. And up to 1.99999, those values are not in the range. You have 2, but not 2.001, just 2. Then starting from 3 and up to 3.99999, not 4. Okay? I would say that no, let it sink in. Keep thinking about it until you are convinced. That is the range. Questions, please ask. Okay? And where is the function increasing? If you look at the graph will tell you it is increasing in 2 parts of the domain, right? From minus infinity to, now when we say increasing, we are not writing the values, y values, we are writing the x values. Okay, it is increasing from minus infinity to 2 union with okay, I'll put it this way, union with 2 to 4. Okay. Actually, okay, sorry. You should put a square bracket here, but if you combine this whole thing, good thing that it is a video. Okay, so you can see it continuously, I can say from minus infinity to 4. Maybe that's even better, right? Okay, so you could divide it into two parts, just because the domain is divided like that. But if you think about it in a different way, it is continuously increasing, from minus infinity to 4, its values are only increasing. Then it's not decreasing anywhere. Now, earlier I was writing D and E. This is one more way of writing. You just show a set, but make it empty. There is nothing. So it is not decreasing anywhere. Okay. I'll write below here. This is an empty set, indicating that the function is not decreasing anywhere. And where is it constant? It is constant from 4 onwards, from 4 to infinity. Okay. Now, some ideas about symmetric functions. Symmetry in functions. If you look at the graph on the bottom right here, the graph is exactly like a mirror image from the x-axis point of view, right? If x-axis is your mirror, then it is a reflection. That kind of graph, we say is symmetric with respect to x-axis. So what will happen if you replace y with minus y, you get the same equation. Okay. So basically for the same x value, you have the y as well as minus y. X comma y and x comma minus y. Both are in the graph. If AB is in the graph, so is A minus B. An example is the function x equals y square. And you can actually see from this what happens. If you take the square, like if you want to get the square root out of this, you will get y is root x and minus root x both. So you get both positive value of y and negative value of y for the same x. Okay, and in such a graph, the line of symmetry is x-axis, of course, right? X-axis is like your mirror or the line of symmetry. And what else I can say? It's actually not a function. Okay, that is one more thing. And I think some of you already know this, right? I think we're talking about in class as well. If you draw a vertical line like that, it intersects at 2 points, so the graph does not pass the vertical line test. So it is not a function. Okay, so let me write that here. Fails the vertical line test. Conclusion is not a function. Okay. The only function that is symmetric with respect to x-axis is the line f of x equal to 0. So that's why there is a star mark here. And there is an underline for the word function, right? So what it is saying is, whenever you have a, this symmetric function with respect to x-axis, symmetric equation with respect to x-axis, it's not going to be a function, except one exception, right? F of x equal to 0. That is basically the x-axis. So what is that? F of x equal to 0. This is x-axis, this is y-axis. If you are saying f of x equal to 0 constant, you are talking about this. This is the line, f of x equal to 0. The y value is always 0. And in that case, of course, it will pass the vertical line test. It will intersect at only one point, but that is just the x-axis. That's the only function which is symmetric with respect to x-axis and is a function. Okay. We have 7 more minutes of recording. So I remembered something. I had told you that in my previous video, okay, the last video of chapter 1, I had mentioned that I'll show you the solution of the last problem on page number 15. Okay, so here is the solution on the right side. Please check your work if you have completed in your notebook. If you have not completed, please don't look at the screen. Complete that by yourself and then check your answer here. Okay. One quick thing here I'll mention is when you add pure water, it's like a 0% solution. Okay. So I had mentioned in my previous video that this is similar to one of the earlier problems. Yeah, it is similar with a slight twist. Okay. The twist is you're adding pure water instead of mixing two solutions like in that sense that both of them had some acid there, but in this case one of the solutions has salt, other has zero salt. In a way you can say it is a 0% solution, and in that sense it is the same problem. Okay. Check your work. Okay, I'll move on and go to page 2 in lesson 2. So the discussion is continuing about symmetric functions. Now we are looking at function which is symmetric with respect to y-axis. Okay, and these kind of functions are called even functions. We will discuss that in a second, why we call them even function. There is a graph you can see here, and because it is symmetric with respect to y-axis now, if there is a point AB on the graph, you will also have minus AB. Understand that. A comma B is on the right side. Minus A will take you to the left side of the y-axis, right? Equal distance, but on the left side. But the y value is same, minus A comma B, at the same height, left and right. If both those points are in the graph, then it is symmetric for every point, In such a graph, here is an example, x square minus 2. And the line of symmetry is, of course, y-axis, whose equation is x equal to 0. Okay. And why are they called even function? Look at this example here. In this example, you see the exponent of x, that's 2, even exponent, right? So even functions are similar to, have similar property as these kind of functions, y equals x square, y equals x to the 4, and so on, even powers of x. Okay. Basically, when you take even power, whether the number is positive or negative, the square becomes positive, right? As a result, it becomes symmetric with respect to x-axis. So whether you plug in minus 3 or plus 3, you get the same result. So the graph becomes symmetric with respect to y-axis. Think about that. Okay. Then there can be another type of symmetry, which is with respect to origin. Okay. Now, this you have to understand a little carefully. Okay. Symmetric with respect to y-axis, that was even function. Now we're talking about symmetry with respect to origin. Now origin is a point, right? This point here, 0, 0 is the origin. So we're talking about two slightly different types of symmetry. In the sense, one of them is across a line, the other one is across a point. So what does that mean? That means if you have any point here, now this is the exact meaning of symmetry. Okay. It means if you have a point x comma y here, you can join that like an arrow, let's say, pointing to that point. Then you can find its opposite by going exactly in the other direction. And that point also is in the same graph. That is the meaning of symmetry with respect to the origin. with respect to origin. Okay, so that means you take any point on the graph, from origin you join a arrow to that point, then from the origin you can just go in the opposite direction of that arrow and go the same length, and wherever you reach, that point also will be on the graph. That is the meaning. That is the exact meaning of symmetry with respect to origin. Okay. Now what happens is, if you go exactly opposite in the direction of that arrow, not only x will be negative, but y also will be negative. So if your original point is AB, then your image will be minus A minus B. Okay, think about that. If you are in the first quadrant, positive, positive, the opposite arrow will take you to third quadrant, like the one that I'm showing here. Now that will go negative x and negative y, right? And same will happen with any other point. And an example is y equals 2 cube root of x. If you know this, cube root means power 1/3, right? That is why they are called odd functions. Okay, they are associated with odd powers of x. Actually, that is cube root of x. Another example I can write here is y equals x cube. That is also an odd function. So one way to distinguish between even functions and odd functions is, for an even function, f of minus x will be the same as f of x, because you are taking the even power. So minus x whole squared is the same as x squared, right? For odd function, f of minus x will be minus of f of x. If you have x cube, then minus x whole cubed will be minus x cube, right? So when you take the negative side, you get the negative result as well. That is odd function. Okay. Moving on. Oh, okay. I think I'm just about out of time for recording. I will continue